All right, welcome to part 3 of chapter 5, diffusion in solids. So we've learned about the mechanism of diffusion, vacancy and interstitial. We learned a little bit about why it's important, and we'll learn a lot more about that as we get into chapter 10. And now what we'd like to do is discuss how we can predict the rate of diffusion. All right, so the rate of diffusion is quantified by Fick's first law. And this equation, which I don't have on here quite yet, but this is getting close, was found experimentally. Okay, so it's an empirical equation. So first what we're going to do is let's just go ahead and define the rate of diffusion. So the rate of diffusion is going to be mass moving through an area per unit of time. So kilograms, meters squared per second, or it might be moles per centimeter squared per second. So stuff per area per time. Okay, that's what we call flux and refer to as J. That's our rate. All right, so the basic experiment then was to take a thin membrane, impose a concentration across the membrane, and then measure how fast molecules of atoms move from one side of the membrane to the other. And what's observed is that the greater this concentration difference, the faster the flux, faster we move things through. And the greater this separation, delta X, the slower we move things through, which hopefully makes sense, right? If we make this twice as thick, then we've got twice as far to move stuff. And ultimately what's important is actually the gradient here. So it's a delta C, delta X, or dC dx. So the flux is proportional to the gradient dC dx, and then all we have to do is put a proportionality constant in between these, and we get Fick's first law of diffusion. And then D here is referred to as the diffusion coefficient, and many times you'll hear me refer to it as the diffusivity. So two names for D, diffusion coefficient or the diffusivity. All right, so you could double check the units here, but D is going to be in something like centimeters squared per second or meters squared per second. C is a concentration, so that's going to be in like kilograms per meter cubed, right? So an amount per volume. And then X, of course, is in meters. So that'll give you a flux of kilograms per meter squared per second. All right, in steady state conditions, the concentration gradient here doesn't change with time. Okay? And so in steady state conditions, this dC dx term then just becomes delta C delta X. So we'll be given the high concentration and low concentration values, and we'll be given the thickness of a membrane. So we can just calculate this. And then given the diffusivity, which simply depends on the material that we're diffusing through, we can come up with the flux. So let's look at a simple example. So here is, let's say we have a pair of gloves and we're worried about the movement of methylene chloride, which is in a paint remover, through the glove. Okay. If we were to use a butyl rubber glove, which is not a good choice, let's go ahead and take a look at that though. We've got a thickness of the glove at about 0.04 centimeters, and we'd like to know how much of this methylene chloride is coming through. Okay, so here's our picture. We have paint remover, we've got a glove protecting our skin, and we've got our skin now in this glove just kind of immersed in the paint thinner. And this is going to be a Fick's first law problem. We're going to assume a linear gradient because the problem is given to us as a steady state problem. Okay, we'll get to non-steady state problems in a bit. So let's say you were to go ahead and use this for a few hours. Let's see what happens with the amount of paint of the methylene chloride that comes through. Okay, so one of the things that has to be given is the diffusivity. So this is the diffusivity for methylene chloride through butyl rubber. Okay, so that's a given, or it's in a table. 110 times 10 to the minus 8 centimeters squared per second. Then we're given the high concentration and low concentration values. These depend on the environment. And we're given the fact that the glove thickness is 0.04. So you can see here, we're just simply plugging in, and we end up with about 1 times 10 to the minus 5 grams per centimeter squared per second. All right, let me just say something about this negative sign here. This negative sign is important, and it refers to the direction of the flux. So when I have a gradient as shown, so this is a negative gradient, right? So we're dropping as we move along in X direction. This is a negative gradient. The flux moves in this direction. It moves in the positive X direction. So that's a positive flux. So that's where this negative comes from. So I have to be careful when I do my delta C term here, right, that I'm doing C2 minus C1. We're always going to assume that our x-axis is positive as it points to the right. So if I was to reverse this picture, put my skin on this side, the paint remover over here, and now my gradient would look like this, which is actually a positive gradient. Okay, I'd still do C2 minus C1. Okay, I get a positive number, I'd end up with a negative flux. Negative flux meaning that my flux is now moving to the left. Okay, so that negative sign is important. You can't just simply get rid of it all the time. It depends upon your coordinate system and how you've chosen to set up your sketch. All right, but let's go ahead and look at this answer a little bit. When it's normalized to an area, it's not clear exactly what this means. So it's consider the glove. If we take a good, medium-sized glove, you can estimate the surface area to be something like 200 centimeters squared. Okay, so if we go ahead and plug that in, and then let's say we're using the paint thinner for 3 hours. Okay, so we'll multiply by 3 hours. We multiplied by 200 centimeters squared. So these units cancel, and we're left with 25 grams, which is quite a bit. All right, so next time what we're going to do is look at the role of temperature, or answer how does diffusion depend upon temperature.